Welcome to the CompTIA A+ Prepcast presented by baremetalcyber.com. Mobile display technologies serve as the foundation for visual interaction with portable devices. The quality, efficiency, and clarity of a display directly affect a user's ability to perform tasks, read content, and navigate the operating system. In the context of the A+ exam, knowledge of display technology is essential, as it appears in domains related to both mobile devices and hardware configuration. The exam expects candidates to recognize different panel types, identify common issues, and understand how specific technologies influence usability and support scenarios. One of the most widely used technologies in mobile and laptop displays is the liquid crystal display, or LCD. This display type relies on a layer of liquid crystal material positioned between two sheets of polarized glass or plastic. The crystals respond to electrical charges by shifting their alignment, allowing or blocking light in precise patterns. Because LCD panels do not emit their own light, they require a separate backlight to make the image visible. This fundamental principle applies to nearly all non-OLED mobile displays and forms the basis for multiple LCD subtypes used across devices. The backlight component in an LCD panel is critical to its operation. Without it, the screen would remain dark regardless of the liquid crystal arrangement. Most modern LCDs use LED-based backlights that sit behind or around the screen to evenly illuminate the display surface. These lights determine the screen's brightness and help define its contrast ratios. Backlight failures often lead to dim screens, flickering images, or entirely black displays. Being able to diagnose whether an issue stems from the backlight or the panel itself is a core troubleshooting skill. In-plane switching, commonly known as IPS, is a subtype of LCD technology that significantly improves upon traditional panel limitations. IPS displays are engineered to allow liquid crystals to rotate within the same plane, which increases consistency in color reproduction and enhances viewing angles. These panels are widely used in high-end tablets, smartphones, and professional laptops, especially where accurate color rendering is essential. IPS technology delivers vibrant images and allows content to remain consistent, even when viewed from off-center positions, making it ideal for shared or multitasking environments. Another subtype of LCD is the twisted pneumatic panel, or TN. TN panels are known for their quick response times, which makes them popular in applications where fast screen updates are prioritized, such as gaming. However, this speed comes at the cost of color accuracy and viewing angles. TN panels often exhibit color distortion or contrast shifts when viewed from the side or top. They are typically used in entry-level or cost-sensitive devices, offering an affordable alternative to IPS displays. While they are functional, they may not provide the best experience for users requiring detailed visuals or color precision. Vertical alignment, or VA panels, are positioned between IPS and TN technologies in terms of performance. VA panels excel at producing deep blacks and strong contrast ratios, making them a good choice for video playback and media consumption. They align liquid crystals vertically when powered off and shift them horizontally when activated. However, they tend to have slower response times than TN panels and narrower viewing angles than IPS. Ghosting or motion blur may be visible in fast-moving scenes. VA panels are often used in mid-range laptops and mobile devices where a balance between visual richness and cost is needed. When comparing IPS, TN, and VA panels, it is important to consider both performance characteristics and user needs. IPS panels provide the best overall visual quality with accurate color reproduction and consistent visibility from multiple angles. TN panels offer faster refresh rates and lower prices, but suffer from image distortion when not viewed head-on. VA panels present high contrast and good image depth, but fall behind IPS in color range and TN in responsiveness. Choosing the right panel type often involves trade-offs between clarity, speed, and affordability. Moving beyond LCD technology, OLED displays introduce a fundamentally different approach to image generation. OLED stands for Organic Light Emitting Diode, and unlike LCDs, these displays do not require a backlight. Each pixel in an OLED panel is composed of organic compounds that emit light individually when electrically stimulated. This allows OLED screens to produce true black by turning off pixels completely and to achieve high contrast ratios with vivid color expression. OLED panels are also thinner and more flexible, which supports sleeker device designs and curved displays. OLED displays offer numerous advantages, but they also come with challenges. Their ability to display rich colors and deep blacks makes them popular in flagship smartphones and tablets. Additionally, because each pixel emits its own light, OLED screens can reduce power usage when displaying dark content. However, these displays are more expensive to manufacture and may suffer from burn-in, a condition where static images leave permanent ghosting. This is especially relevant when user interfaces display the same elements for extended periods. Technicians must be aware of these limitations when selecting or replacing OLED panels. Display technologies are not interchangeable, and knowing which type is used in a device affects both configuration and repair. The exam may include questions that require comparing panel characteristics or matching a display type to a specific use case. For example, a question may ask which panel type offers the best viewing angles for a tablet, or which technology is most prone to motion blur. Understanding how panel types differ in structure, behavior, and performance enables better decision-making during support scenarios. Active matrix OLED, commonly known as AMOLED, is an advanced subtype of OLED technology. It incorporates a thin film transistor layer that controls each pixel more precisely, enabling faster refresh rates and improved response times. This results in smoother motion rendering and better energy efficiency, especially in high-resolution or high-refresh mobile displays. AMOLED panels are widely used in flagship smartphones and premium tablets where display performance is a primary selling point. Many AMOLED displays also integrate touch sensitivity directly into the display layer, reducing the need for additional components and allowing for thinner device designs. Comparing LCD and OLED technologies involves weighing several important trade-offs. LCD displays tend to be more durable, less expensive, and have longer lifespans. They are also less susceptible to image retention or burn-in, making them suitable for devices that display static content for long periods. OLED displays, on the other hand, offer superior contrast, wider color gamut, and thinner profiles. Their ability to completely turn off individual pixels allows for true black reproduction, which is not possible with backlit LCDs. However, OLEDs are more fragile and costly to produce, which influences repair strategies and replacement part selection. The A+ exam may test a candidate's understanding of several key display characteristics. These include screen resolution, panel type, refresh rate, and response time. Brightness and contrast ratios also appear in questions related to display selection or troubleshooting. Candidates must be able to recognize visual artifacts like dead pixels, flickering screens, and uneven backlighting. In some cases, scenarios may require matching a display type to a specific user need, such as selecting a color-accurate panel for a content creator or a fast response panel for a gaming laptop. Resolution terminology is another topic that often appears in display-related exam questions. Terms like HD, Full HD, Quad HD, and 4K describe the number of horizontal and vertical pixels on the screen. Higher resolutions offer greater image clarity, but may consume more power and require more powerful graphics processing. For mobile devices, the balance between screen clarity and battery life is especially important. Understanding resolution differences helps technicians advise users on device selection and troubleshoot performance or display scaling issues. Modern mobile devices often include integrated touch capabilities within the display panel. These may use capacitive sensing or active digitizer layers, depending on the device's intended use. Capacitive touch is common in smartphones and tablets, allowing for multi-touch gestures and rapid response. Digitizers, often used with styluses, are found in convertibles and drawing tablets. Integrating touch functionality directly into the display reduces device thickness and enhances responsiveness, but it can also complicate replacement procedures and increase part costs. Replacing a mobile display panel typically requires careful disassembly, beginning with bezel or case removal. Internal display cables must be disconnected without damaging connectors or surrounding components. After removing the old panel, a replacement must match the original specifications in size, resolution, connector type, and panel technology. Anti-static tools should always be used during disassembly to prevent component damage. Because displays are sensitive to both electrical and mechanical stress, technicians must follow manufacturer guidelines closely when performing replacements. Troubleshooting display problems includes recognizing common symptoms such as flickering, dim images, color distortion, or screen artifacts like lines and dots. Dead pixels may appear as persistent black or white dots, while backlight failure results in a dark but powered-on screen. Loose cables or failing connectors can lead to intermittent display loss or scrambled output. Technicians should test with external monitors to isolate whether the issue is panel-related or due to graphics hardware or software drivers. External display configurations are another area of interest for both users and the exam. Mobile devices often include HDMI DisplayPort or USB-C outputs that allow connection to external monitors. These outputs can be configured for mirrored or extended displays, and scaling settings control how resolution and text size are adjusted. Display output management is typically handled through the operating system's display settings panel, where users can select which monitor acts as the primary or adjust orientation for different setups. Power usage is a critical concern with mobile displays, especially in battery-powered environments. High-brightness screens and high-resolution panels draw more power and can reduce battery life significantly. Many operating systems include adaptive brightness features and allow users to configure sleep timers or display dimming settings to conserve energy. Reducing resolution or refresh rate, when supported, may also extend battery life. The A+ exam may include questions about how display settings affect power management and what steps can be taken to optimize usage. In conclusion, mobile display technologies encompass a wide range of panel types and characteristics, including LCD, OLED, IPS, TN, and VA. Each type has specific advantages, disadvantages, and use cases, and technicians must understand how to identify, compare, and support them. The A+ certification covers display types, failure symptoms, troubleshooting methods, and replacement procedures. Familiarity with these topics prepares candidates to handle real-world display issues and ensures success when addressing related exam objectives. Thank you for listening. Please visit baremetalcyber.com for more cybersecurity information, podcasts, books, and more.